In this lesson, we'll do a few example problems using the fundamental theorem of calculus part 1. Before we do our examples, let's remind ourselves what the theorem says. So it says if we take this function capital F of x, which is the definite integral from some constant a to the variable x of f of t dt, and again this function represents the area, so capital F of x is the area between the graph of y equals f of t and the horizontal or t-axis from a to x. So capital F of x represents this area from this constant a to the variable x. So our fundamental theorem tells us that the derivative of this function capital F is our inside function little f evaluated at your variable x. So let's do a few examples. Here we have capital F of x is the integral from -2, so a constant, to x sine of t dt. So this fits our theorem. So our derivative is equal to our inside function, so the sine function, evaluated at our variable x. So we get sine of x for our derivative. In our next problem, we have the definite integral from 0, so again a constant, to x, of the square root of 1 plus t squared dt. So again, we just apply our fundamental theorem, which tells us that the derivative g prime is equal to our inside function, which is this square root function. So we get the square root of 1 plus, and it's evaluated at our upper variable x, so 1 plus x squared. So again, whenever we have integral from a constant to x of a function, the derivative of that is just your inside function evaluated at your variable x. In this example, we have capital F of x is the integral from x to 2 of t squared dt. So the first thing we should notice here is that we're not exactly in the setup of our fundamental theorem because we have integral from x to 2. So here x is our lower limit of integration and our constant 2 is our upper limit. So the first thing we need to do here is switch the order of integration. Remember, when we do that, we introduce a negative sign. So this becomes negative integral from 2 to x of t squared dt. So we're using one of our properties of the definite integral here, which is that the integral from a to b of f of x dx is equal to negative integral b to a. So if we switch the order of integration, then we get a negative sign. So now we can just take our derivative because now our integral 2 to x fits the mold of our fundamental theorem part 1. The negative is just a constant multiple that stays out front. So we get negative and then our inside function, so evaluated at x, so we get negative x squared for our derivative. So our key for this one was that we had our constant and our x switched relative to the fundamental theorem, so we had to switch the order, which gave us this negative sign. Let's do one final example. Here we have integral 0 to x squared cosine u du. So we have our constant in the lower limit, so we fit our mold, but we don't have an x, we have an x squared. So that means we have a composition of functions here. So we have a function of x in our upper limit. So our derivative here will be our inside function, which is cosine, and then we're going to evaluate it at this upper limit, so x squared, but the chain rule tells us that since we don't just have an x here, we actually have a function x squared. Chain rule tells us we have to multiply by the derivative of the inside, which in this case is 2x. So again, the new part for this problem was that we first applied our fundamental theorem part 1, but then because we had a function x squared in our upper limit, we had to use the chain rule, which tells us to multiply by the derivative of that inside function. And the derivative of x squared is 2x.